the explanation has been something else. Recommended as the previous hypothesis, countless impacts on various evaluations, besides being produced by a large number of analysts, provide evidence to support this idea. The attestation of the nature of the universe started the current universe anyway. Science and new developments bring us new perspectives and assessments. These tests put us in new positions, from a point of view where specific data points, like the ones from Neil deGrasse Tyson, have grown into a significant figure in influencing the science now universe. With that, something is drawing in, the James Webb Space Telescope. It is fundamental to comprehend something that could put our faith in the hypothesis. The James Webb is being launched by the universe. The Space Telescope has discovered 750 systems that are not exactly universes, unrecognizable from our expectations, causing us to reconsider our assumptions. We were aware of them in some way. This discovery should help us recognize the transformation of massive systems, so it is not surprising that it makes us think about how we might have the choice to relax the universe. Prior to this, agents declared that the Big Bang hypothesis was an excellent explanation for the way the universe began. According to this theory, the universe began 13.8 billion years ago. It emerged via a confounding event, such as the absurd tale of the introduction of the universe. Regardless, the James Webb Space Telescope has tested this. I believe these images depict universes that are smoother, more subtle, and seasoned, to put it mildly, but not quite identical to the hypothesis of how things transpired. In accordance with speculation, as space and time expand, things ought to appear more discernible despite being further away. These extravagant designs try to keep that standard, according to the hypothesis. In the true beginning of the universe, everything that existed was condensed into 1 second, an extreme, supersonic point, also known as a singularity. This anomaly was unimaginably hot, greater than anything we could truly measure or construct. Numerous factors contribute to this singularity. According to Albert Einstein's general relativity, within this singularity, everything in the universe was destroyed into a small area with a very high density, a staggering amount of mass and energy packed into a tiny space. In simplest terms, professionals have repeatedly stated that this hypothesis explains how things got their start. The universe began, anyway, with these new images from the James Webb Space Telescope. We are now being questioned about that. The universes it discovered did not fit with what was anticipated by the hypothesis and the early explanation for the universe's formation. The universe may not be as stable as we thought. We see that every ounce of energy in the universe began in a very hot and dense point, known as a singularity. This singularity served as the early stage for everything we currently see in the universe. The universe was altered by this singularity. It started to develop and evolve over roughly 13.7 billion years to achieve its current state. Expansion began with something that many refer to as the immense expansion, during which the universe grew rapidly, substantially faster than the speed of light. This rapid expansion shaped the universe by creating and making things more uniform. It allowed stars and galaxies to influence the formation of structures. As the universe continued to grow, its expansion slowed compared to the extraordinary initial inflation, yet it continued at a steady pace. Experts have witnessed evidence of this expansion through factors such as redshift, the shifting of light from distant galaxies. So now, as we take in the stunning photographs of new galaxies captured by the James Webb Space Telescope, it is somewhat surprising for inspectors. These images do not correspond to their theoretical predictions. This discrepancy presents a problem. Many of these galaxies appear significantly more mature than anticipated, which casts doubt on our perspective of the evolution and structure of the cosmos. According to the Big Bang hypothesis, the number and distribution of galaxies should follow a specific pattern. However, the first images depict a staggering number of galaxies, far more than expected. This discovery has led experts to question whether some of the hypothesis's estimates are accurate. In any case, specialists are beginning to reconsider their models, as these revelations challenge their existing theories. One of the most incredible aspects of these new galactic structures is their perfection, which contradicts the hypothesis of how early galaxies should appear. According to theoretical models, early galaxies should exhibit irregularities in their shapes and structures due to their chaotic formation and evolution. However, images from the JWST depict galaxies that are very smooth, lacking the expected roughness and complexity. In the early universe, everything was compressed into a tiny space. As the universe expanded, particles underwent changes as they cooled. Electrons, neutrons, and protons began to interact with light and energy, shaping the matter in the universe. Within the first few minutes after the Big Bang, a process called nucleosynthesis led to the formation of lightweight elements like helium and hydrogen. These elements set the foundation for the formation of stars, galaxies, and the more complex structures that followed. As the universe expanded and cooled, gravity played a crucial role in shaping its structure. Matter began to clump together, forming dense regions that would eventually become galaxies, stars, and planetary systems. The first stars, known as population 3 stars, were massive and short-lived, burning through their fuel quickly before exploding in supernovae. These explosions enriched the universe with heavier elements, which later contributed to the formation of new stars and planets. However, the observations from the James Webb Space Telescope challenge some of these long-standing assumptions. The galaxies it has captured appear too mature, too structured, and too numerous for the timeline predicted by the Big Bang theory. If these galaxies formed so early in cosmic history, it raises questions about whether our understanding of galaxy formation is incomplete or if new physics is needed to explain these anomalies. One of the biggest surprises is that these galaxies do not seem to follow the expected timeline of gradual development. Instead of appearing as chaotic, irregular, and primitive structures, they show signs of organization and stability. This has led some scientists to speculate that perhaps the universe is older than we think or that our models of early cosmic evolution need to be revised. Moreover, the telescope's findings have sparked debates about the rate of expansion of the universe. The current standard model relies on a value known as the Hubble constant to describe how fast the universe is expanding. But discrepancies between different measurements of the Hubble constant, one based on the cosmic microwave background radiation and another on observations of galaxies, have already raised concerns. Now, the discovery of these unexpected galaxies further complicates the issue. Some researchers have proposed alternative explanations. Could there be an unknown force or process influencing the formation of galaxies? Is it possible that dark matter or dark energy plays a more significant role than previously thought? Or could it be that our understanding of gravity itself needs to be modified? The James Webb Space Telescope continues to provide groundbreaking insights, pushing scientists to reconsider the foundations of cosmology. While the Big Bang theory remains the leading explanation for the origin of the universe, these new findings suggest that our knowledge is still incomplete. Future observations and new theoretical models may help bridge the gap between existing theories and the surprising realities revealed by Webb's images. As scientists analyze more data, they hope to uncover answers to some of the universe's biggest mysteries. The coming years may lead to revolutionary discoveries that reshape our understanding of cosmic history, the formation of galaxies, and the true nature of the universe itself. This blend of essentials was revealed by history, one of the fundamental stages in the universe's development. Moving forward from an initial state of particles and energy to the point where matter started to structure, in accordance with the hypothesis of the ancient Big Bang, scientists had anticipated seeing universes that were dispersed and turbulent. However, the first images tell a different story from the expected chaotic one. Photographs of dispersed universes reveal smooth, winding, and round shapes resembling the structures we find in the present-day universe. These alarming discoveries challenge the belief that chaos is a common occurrence in world development. If there aren't many, or any, turbulent events happening in these universes, as suggested by the hypothesis, it raises the question, how did structure emerge? It becomes irrational to assume that even the tiniest of universes would be able to grow into massive structures, as anticipated by the expanding universe theory. According to this theory, objects appear smaller as they move farther away due to expansion. However, experts have observed a striking phenomenon: enormous structures frequently congregate in large social groupings, forming patterns that span across the cosmos. The large-scale structure of the universe aligns with hypotheses about its origins. The widely accepted theory suggests that the universe began in an extremely hot and dense state, then expanded and cooled over time. The role of gravity in shaping matter and organizing cosmic systems is consistent with predictions made by the Big Bang theory. Matter, influenced by gravitational forces, forms interconnected structures known as cosmic filaments, an incredible web-like presence of galaxy groupings. This large-scale distribution of galaxies strongly supports the idea that the universe started as a dense state and expanded over billions of years. Recent images from the James Webb Space Telescope, JWST, challenge some of our previous assumptions. We thought we understood the evidence supporting the Big Bang hypothesis, that small galaxies should form and expand through interactions and mergers. However, the galaxies observed by JWST appear different from these expectations. Scientists had assumed cosmic structures would show clear signs of convergence, collisions, and mergers, yet the images suggest otherwise. Despite these unexpected findings, the Big Bang remains an extraordinarily significant theory, not just speculation. It is supported by undeniable evidence, such as redshift observations of distant galaxies, which indicate the universe is expanding. The steady separation of galaxies over time aligns with the predicted expansion of space. Additionally, the cosmic microwave background, CMB, serves as crucial evidence for the Big Bang. The CMB is a faint glow of radiation that permeates the universe, a remnant of the early universe's hot and dense state. First detected in 1965, this ancient light continues to match theoretical predictions. The temperature and uniformity of the CMB strongly support the idea that the universe once existed in a hot, dense state before undergoing rapid expansion. The discovery of the CMB provides a unique window into the earliest moments of the universe. As a direct remnant of the initial stages following the Big Bang, it helps scientists determine the origins and evolution of the cosmos. As researchers continue to analyze data from the James Webb Space Telescope, JWST, and other advanced observatories, they seek to refine our understanding of cosmic evolution. While unexpected findings challenge certain aspects of our models, they also open new avenues for exploration. Science thrives on questioning, revising, and improving theories based on new evidence. One area of active research involves dark matter and dark energy, which together constitute approximately 95% of the universe's total composition. Despite their significant influence, these mysterious components remain largely elusive. Scientists infer the presence of dark matter through its gravitational effects on galaxies, yet it does not emit, absorb, or reflect light, making direct detection incredibly difficult. Similarly, dark energy is believed to drive the accelerated expansion of the universe, yet its precise nature remains one of modern cosmology's greatest mysteries. The quest to understand the cosmos extends beyond theoretical models. Ongoing and upcoming missions, such as the Nancy Grace Roman Space Telescope and the Euclid mission, aim to provide deeper insights into dark matter, dark energy, and galaxy formation. By mapping the large-scale structure of the universe with unprecedented precision, these projects will help refine our cosmological theories and test the limits of our understanding. Additionally, the study of gravitational waves, ripples in spacetime caused by violent cosmic events, has opened a new frontier in astrophysics. First detected in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, these waves confirm predictions made by Einstein's general theory of relativity. Continued gravitational wave observations allow scientists to probe black hole mergers, neutron star collisions, and even potential clues about the early universe. Despite the many unanswered questions, the scientific method ensures continuous progress. Each new discovery, whether confirming or challenging established models, brings us closer to unraveling the mysteries of our cosmic origins. The history of the universe is written in light, gravity, and the fundamental forces that shape existence. By studying them with ever-advancing technology, we continue to refine our place in the grand cosmic story.